In this lecture, we're going to start talking about how do we deal with loops from a hydraulic perspective. We've now covered single pipes, single minor losses systems that include pipes and fittings in series and in parallel. We covered a branching case, and now we come to loops, which is the most complicated of the situations we come to. First, we need to give ourselves a couple additional tools. So I've written here up in the upper left, you can see Darcy-Weisbach equation. I haven't shown you all the details, but by doing some substitutions into Darcy-Weisbach, I can show that you can rewrite it as I do on the right hand side. 8FL over pi squared g d to the fifth. So I've just substituted in, for example, Q equals AV. So for V there, I've substituted in Q over A. I've put in then the formula for the area of a circle and so forth, and I wind up with this. And then the next one down, you can see Hazen-Williams equation, where all I've done is really just taken the QCFS and put it over here. In both of these cases, you can see that they're both in the general form H sub L equals K Q to the nth, where K is some big thing, right? You can see it's this first part up here and this first part up here. Q, the flow rate, and then to some exponent n. So if I'm using Hazen-Williams, if I'm using Darcy-Weisbach, then K is equal to 8FL over pi squared g to d to the fifth, and n equals 2. If I'm using Hazen-Williams, then K is equal to, we're going to say it's phi, this is going to wind up being a constant in a minute, L over C to the 1.85 D to the 1.85, sorry, D to the 4.87, and N is going to be 1.85. Okay, for Hazen-Williams, this phi is going to be 4.73 in US units, and phi is going to be 10.66 in SI. Okay. Note that D is in feet here in Hazen-Williams, meters in SI, and in length is feet in US and meters in SI. And Q, this is the CFS form, or CMS, cubic meters per second in SI. Okay, so we're going to use this again in a little bit, but the main thing we're going to talk about with regards to how are we going to solve loops is a method called the Hardy-Cross method. There are other methods than this one, but this is a standard one that most civil engineers learn, and it was the main method used for this for a long time, even though there are now new algorithms that may be better in certain circumstances. This is very similar to what EPA-NET, for example, is doing in the background when you ask it to solve a system. So useful for loops and networks. It assumes, basically the steps are, we're going to assume some flows in all the pipes, and then we're going to correct those flows based on two principles. Both of which we already kind of know. One is that the flows entering a junction are equal to the flows leaving a junction. Okay, this is just continuity. And 2, that the sum of all head losses in a loop has to be equal to 0. That is to say, if I have a very simple loop, I'm just going to draw right here, I've got maybe some flow entering at this point, and maybe I have some flow exiting down here, some flow exiting down here, maybe some flow exiting down here as well. If I take any point on here, say this starting point up here, and I take the head loss through this pipe, the head loss through this pipe, the head loss through this pipe, and the head loss through this pipe, I should get back down to a 0 head loss. Okay. How do I do that? Well, let's say I had a head loss here of 2, here 1, here 3. Okay, so if I have a head loss of 2 to here and 1 to here and 3 to here, I've accumulated 6 feet of head loss by the time I get around to the lower left. To get back down to 0, I can't like add head, but what this would mean is that the flow must be going this way, and that it would lose 6 feet of head to get down here. Because this point in the lower left and the point in the top left, there's sort of 2 parallel ways that you get from the point in the top left to the bottom left. One is around the right hand side, and the other's on the left side. And we know that the head loss around those two parallel paths has to be the same, right? So if I get 6 going around to here, I have to get 6 this way, right? Which means if I like add this 6 and subtract that 6, I get back down to 0. You'll see how that kind of plays out in a little while, but the point is, because there's only one value of head at every point in the loop, as I add and subtract head losses around the loop, I should get back down to where I started. Therefore, the sum of all the head losses in a loop is 0. More on that in a little bit. Okay, so what is our governing equation? Our governing Hardy-Cross equation is going to be that delta Q is equal to negative summation kq to the nth divided by n times the summation of the absolute value kq to the n minus 1 and absolute value for each loop. Okay, so what we said was we're going to assume all the flows in all the pipes. We're going to make an assumption of what they are. Then we're going to use this formula to calculate delta Q. How should we change our assumed flow rates in that loop? And then we're going to iterate. So we make an assumption, we calculate delta Q, gives us new flow rates, our assumptions plus or minus our delta Q. Then we're going to calculate this again, and we'll keep going through that way. Note that the top of this equation, the summation kq to the nth, we just talked about how head losses can be expressed as kq to the nth. When I say the summation of kq to the nth, I'm saying what is the sum of all the head losses in that loop? Well, we said the sum of all the head losses in the loop should be 0. That was our second principle. Thus, if I calculate delta Q and the sum of all the head losses in the loop is 0, my delta Q is going to also be 0, in which case I'm done. When I do a new iteration, I won't see any change in the flows, and I'm done. If the sum of all the head losses in the loop is not 0, I'm not done. I'm going to get a non-zero delta Q, and I'll be able to iterate again. The denominator is just a kind of a scaling factor to help us figure out how much of a correction gets applied. So iterate until delta Q is about 0. Okay, so let's look at this. I recommend you take a minute and maybe pause the video and draw this network out. We're going to first go through in general what are the general steps for the Hardy-Cross method. So I'm going to write those out on here while we're looking at this, this loop. And then once I've written out what the general steps are, we will go back to it and actually apply it as we solve the problem. Okay? All right. Step 1, Hardy-Cross method. Determine a value for n. Remember, Darcy-Weisbach, n equals 2, Hayes and Williams, n equals 1.85. So are you going to use Darcy-Weisbach or are you going to use Hayes and Williams? Step 2, arbitrarily select a positive direction. Clockwise or counterclockwise. Usually I select clockwise as positive. We'll see that in a minute. Step 3, label all branches and junctions in the network. So give them names, numbers. 4, we want to separate into loops so that each branch is in at least one loop. If you look at our network up at the top, there's multiple ways that we could do this. The obvious way is we could make a loop that sort of goes around this way and one that goes around this way. Everything would be in one then. We could also do one that goes around all the outside, but that doesn't have this pipe in the middle, so we'd need another loop that would get at least that pipe in the middle, and now everything's in a loop. So multiple ways to do it. Step 5, we want to calculate K for each branch / pipe. Right, we just said we could express head loss as KQ to the nth. K is just a bunch of stuff that's specific to each pipe, diameter, length, friction factor, etc. So we want to calculate K for each branch and pipe. 6 is where we assume reasonable flow rates and directions for each pipe. You'll see in the example that here we want to make sure we meet our first criterion, that flows entering a junction equal flows leaving a junction, when we make these initial assumptions. Number 7, we're going to calculate delta Q for each loop. And number 8, apply the delta Q to each branch in each loop. Step 9, repeat until delta Q is about 0. And that's it. Now there are nuances associated with some of these, especially for number 8, how you apply the delta Q to each branch in each loop, that we'll talk about in the example in just a second. But these are the general steps. Now let's look at this particular problem and actually go through and solve it. Hang on. Okay, so here we are in the problem. Let's go through and do it. Step 1, we have to determine the value of n. We are going to use Darcy-Weisbach for this. So Darcy-Weisbach n equals 2. Next, step 2, we're going to assume a positive direction. Okay, we're going to assume clockwise is positive. Step 3, label all the branches and the junctions in the network. Okay, so we're going to call this pipe at the top pipe 1, this one over here 2, this one 3, this middle one 4, this bottom one 5, this one on the left we're going to call 6. The arrows are not pipes, they're just sort of demands or like flows entering or leaving the system. And then our nodes, we'll call this one on the top left A, top B, top right C, bottom D, bottom left E. Done. Step 4, we want to assign our loops. So we're going to have 2 loops, loops 1 and 2, Roman numeral 1 and 2. 1 is going to look like this on the left hand side. 2 is going to look like this. Step 5, I'm going to do this one over, let's do it here, step 5. Okay, this is going to take a bit. We're going to calculate K for each branch in the network. So what I like to do is make a nice organized table here. So I'm going to start doing that. I'm going to put across the top the headings. We've got our loop. We've got our pipe. We've got the diameter in inches, diameter in feet, the length, the friction factor, and the calculated value of K. Leave some space over it on the right hand side that we will use later. So we've got loop 1. In loop 1 we have pipes 1, 4, 5, and 6. And then in loop 2 we have pipes 2, 3, and 4. The diameters in inches, I'm just going to pull these from the diagram. 4, 8, 8, 4. And this is 5, 6, 8. In feet, 0.33, 0.66, 0.66, 0.33, 0.416, 0.50, and 0.66. My lengths are 2,500, 2,000, 1,500, and 3,000. Loop 2, 3,500, 6,000, and 2,000. F is 0.02 all the way down. We're given that at the top of the screen. And now I can calculate my value of K using the formula that we talked about at the beginning of class. I'm going to write this line a little bit further over here in a minute. So for Darcy-Weisbach, it was that 8FL K equals 8FL over pi squared G d to the 5th. And so all those values are here in the table other than G and pi. But K winds up being for pipe 1, 306. For pipe 4, it's 7.7. Pipe 5 is 5.7. Pipe 6 is 367.4. Loop 2, pipe 2, 140.5, 96.8, and 7.7. Okay, we're done with step 5. Now we're on to step 6, where we're going to assume reasonable and consistent flow rates in each branch. Okay, so we start at point A. We have 1.5 CFS coming into there from that arrow on the left. So we have to make some assumptions about what's leaving. I'm going to say I want to assume about half goes one direction, about half goes the other direction. So in this pipe 1, I'm going to put a little flow arrow there, and I'm going to put 0.7. And then down here on this pipe 6, I'm going to put a flow arrow pointing down and assume 0.8. Thus, I have 1.5 coming into junction A, and I have 0.7 plus 0.8, or 1.5, leaving junction A. Seems like a reasonable starting assumption. Now I go to junction B. I've got 0.7 coming in. I'm going to make a similar assumption again, that about half, or 0.4, goes down out of there. And over here in pipe 2, the other 0.3 winds up going to the right. So 0.7 entering, 0.7 leaving. Now I get up to junction C. I've got 0.3 coming in from the left, and I've got 1.0 leaving to the right. So now I know what must be in pipe 3. I have to have 0.7 coming from there to make continuity work at junction C. I go down to junction D, and same thing. I've got 0.4 coming in and 0.7 leaving. Thus down here, I need 0.3 coming into junction D from the left. And now I check junction E. I've got 0.8 coming in, and I've got 0.5 leaving to the left, 0.3 leaving to the right, so I'm good. Step 6 is done. Step 7 is to calculate delta Q. All right. So what I'm going to do now is, in the space to the right of the table I've already made, I'm going to make some more entries. First, Q, what is the flow that I assumed in that pipe? Next, KQ to the nth. And then next, absolute value KQ to the n minus 1. And last, delta Q. So my assumptions for flow started at 0.7 for pipe 1, 0.4 for pipe 4. Now here's where it can get a little tricky. I've assumed a direction that's positive, and you can see that in loop 1, for example, I have my clockwise circle there, loop 1. You can see the assumed flow in pipe 1 is going in the direction that I assumed was positive in loop 1. In pipe 4, where I assume 0.4 CFS is going down, that's also going in the same direction that my loop here for loop 1 is going. But when I get to pipe 5, the flow is going to the right against where this kind of clockwise loop is pushing. So instead of calling that a flow of 0.3, I'm going to call it a flow of negative 0.3 because it's going against my convention. For pipe 6, same thing, it's going against, so I'm going to call it negative 0.8. Now this is where there's a couple different ways people do Hardy-Cross. This is the way I do it. You can do it where all the flows remain positive and you deal with the negative issues later on, but this is the way I'm going to do it. And as long as you're consistent, you can do it either way, but this is the way I'm going to teach you. Okay, we get to loop 2. Pipe 2 is 0.3 because it's going with the positive direction, but I get to pipe 3 and its flow is going against the convention. So we have negative 0.7 and then we get negative 0.4 for pipe 4. Note, pipe 4 in loop 1 has a positive 0.4 flow because it's going with the convention. In loop 2, the convention's coming back up that pipe, but the flow is going down, and thus as a negative 0.4 in loop 2. Okay, now for kq to the nth and kq to the n minus 1, I'm just calculating it based on all the values that are already here. I'm running out of space a little bit, so I'm going to try my best. 149.9, 1.23, negative 0.513, negative 235.1, and then we go down and we're at 12.65, negative 47.4, and negative 1.232. Okay, now for the absolute value, kq to the n minus 1, I get 214.1, 3.075, 1.71, 293.9, 42.2, 67.7, and 3.08. Okay, so now I'm to the point where I can calculate my delta Q's. So for loop 1, delta Q, remember my general equation, delta Q is negative sum kq to the nth over n sum kq to the n minus 1. So I'm going to do for the entire loop, for loop 1, we get the summation of the negative summation of all the kq to the nths. My kq to the nths are shown right here. Kind of looks like California. I'm going to sum all those together, and I get a value of negative 84.5. Okay, and I might as well do the rest while I'm here. If I sum these, when I get to loop 2, I'm going to sum those, and I'm going to get negative 35.98. In the denominator, I'm going to be summing all the kq to the n minus 1s, so this guy winds up being 512.8, and then this one is 112.98. So back to loop 1, negative summation kq to the nth, that's going to be a negative 84.5 divided by n, which is just 2, times the summation of the kq to the n minus 1 absolute values, which we said was 512.8. Okay, 512.8, we're back. If I do that, I get positive 0.08. Okay, I go down to loop 2, do the same thing, delta Q equals negative, I got negative 35.98, negative 35.98, all over 2 times my 112.98. That equals a positive 0.16. Okay, that was step 7, calculating the correction for each loop. Now we're moving on to step 8, where we're going to apply the correction to each branch in each loop. And here's where it can get a little bit tricky. Okay, so hang on. We're going to move this up so we have a little more space. So for some, it's pretty easy. We've got pipe 1. Let's just look at that as an example. Its Q value was 0.7. My delta Q, if I look over here on the right side of this table, for loop 1 is going to be 0.08 for all of these. So 0.7 plus 0.08, I get a new value of 0.78 CFS. So for my next iteration, I'm going to start with a flow of 0.78 in pipe 1. Pipe 4, we're going to skip for a second. I'll show you why in a minute. Pipe 5, we had negative 0.3, we add 0.08, and we get negative 0.22 CFS. It should be the case that I'm maintaining continuity through here, and we'll show this in a minute, but yeah, I'll go back and show it in a minute, but if you look at junction B, you can see we're trying to maintain our continuity here. Pipe 6 was negative 0.8. I add 0.08, and I get a negative 0.72 CFS. Pipe 2, we get to loop 2, its correction over here in the table is 0.16, 0.16, and 0.16. Pipe 2 was 0.3, we add 0.16, and we get 0.46. Pipe 3 was negative 0.7, we add 0.16, we get a negative 0.54. Okay, the trickiest part is pipe 4. Pipe 4 is included in both loops, and so we have to apply both corrections at the same time. The trick is the sign on those corrections. So we look at pipe 4. In the top, pipe 4 has a flow of 0.4, and in the bottom, in loop 2, it has a flow of negative 0.4. So let's just think about it as if we're doing loop 1, where we start with 0.4 CFS. We're going to add the 0.08 CFS correction. That's the delta Q from loop 1. The trick here is now we have to subtract the 0.16 correction in loop 2. Okay? Because pipe 4 is in both loops, in one it's going with the flow, in the other it's going against. In the loop that it's going against, I have to subtract the correction. I have to put a negative sign on whatever the correction is. If the correction had a negative sign, then I would be adding that correction instead of subtracting it. Okay, so I'm going to subtract off 0.16, which is the delta Q in loop 2. And when I do all that, I get a value of 0.32 CFS. So for pipe 4 in loop 1, its new flow would be 0.32 CFS. In pipe 4 in loop 2, its new value would be negative 0.32 CFS. If I did this all right, I should see that continuity is still maintained in the overall system, even after this whole first iteration. And the way I did pipe 4 here, this is where different versions of the Hardy cross differ. If I assumed all the flows were positive, even those that were going against my convention direction, that's where I would introduce a different rule here. But the way we're doing it, where we're just putting the negative sign already on the flow, all I have to do is apply the correction with the sign that is given to it, as I did, except in those pipes that are shared, in which case I'm going to use the sign on the correction if the assumed flow was in the same direction as my convention that's positive, clockwise in this case, and I'm going to subtract or put the opposite sign on it if the flow is against my convention, as it was in pipe 4, loop 2. Okay, now that I have this new set, I would just basically go through and do the whole thing over again. And I would keep doing that until these corrections that I'm calculating, these values of delta Q, are sufficiently small that I'm happy and I'm just going to be done. Okay, so that is all for this lecture. And the next step will be to talk about what happens if we introduce pumps or if we introduce fixed head nodes like reservoirs into our system. But for now, this is the process.